in the frequency domain. We saw that we have an array of sensors. Okay, so for each frequency we measure the signal in each sensor for each frequency. And then we have Y2F and so on until we have YMF. So we have M sensors, and then we process the signals for each frequency independently. So our model is that YMF equals to some vector which is multiplied with the desired signal. Okay, so it looks like that. XMF, which is the desired signal in that sensor, plus the noise. And we saw that we can write it as the relative transfer function. We can write it as GMF divided by G1F X1F plus VMF. So this is the relative transfer function, which we saw we can estimate it from the observed signals under certain conditions. And then we saw that we can define a vector. So this vector contains the measurements from all the sensors. So we have Y1F up to YMF. Transpose. So this is vector of measurements for the frequency F. And from this vector of measurement, we want to estimate the desired signal in the reference channel, in the reference sensor. Okay? So we can write this as equal to a vector of M measurements. Let's write it like this. But because the desired signal is correlated. Okay. But because the desired signal in different sensors is correlated, it's okay? Backward? Like this? Yesterday it was okay. Maybe we need light. Maybe the light will help. Okay, well, you are the professional. Okay, just whatever you say. Okay? So when we have this model that the measurements, vector of measurement, m measurements, the number of sensors for each frequency f, it equals to the desired signal in the vector of sensors, plus noise in the vector of sensors. But the advantage is that we can write it in such a way that it is related to the desired signal in the reference sensor by writing it like this. D, which is a vector, D f, multiplied with a scalar, x1f, plus vf. Okay, so if we write it in such a way, so when we go from here to here, we assume that we know this vector. Either we know it, we know how to estimate it, and then it gives us a lot of information. Actually, this is called the steering vector or propagation vector. And we can obtain it actually from the measurements of the coherence function between x and x. Okay? So we saw that D, the steering vector, equals to the coherence. So I want to use the same notation that we used before, okay, just to check, because you need to be consistent. See, so it was here. Let me check. Okay, so it was here. This is the model. And we saw that the vector, this vector, which we assume that we know, it contains a lot of information. We know the direction of the signal, but not only the direction. We know, including all the reflections from the desired source to each of the sensors, which is a lot of information. So we know this relative transfer function. And this relative transfer function is actually, you see, equals to the correlation or the gamma, the joint complex conjugate between x1 and the vector x. Okay, I have it here. This is an element here. See? And this, suppose that we measure in the sensor array, we have measurements of the correlations between x1 and x. It's called the coherence function, or partially normalized coherence function, which we can measure that or can estimate it once either from noisy measurements or even better from clean measurements using the sensor array. So we have that this is the way it is defined. So actually, this propagation vector or steering vector or coherence function, partially normalized coherence function, all similar names. It depends on the application where you use it. But what you need to understand, that this contains a lot of information. First, where the source, the desired source, which direction it comes from. Also, reflections in the environment. If it includes reflections, it will include in the transfer function or relative transfer function. And also, it depends on the configuration of the array, where you put the sensors in the environment. So all of that information, we use it in this vector. And then we try to estimate this scalar, which is the component of the desired signal in the reference sensor. So we can try to obtain an estimate of x1f from this vector of noisy measurements. That's why it looks like that. linear filter. Okay? So we saw that we can write it like this. So we need to find an optimal filter of length m. For each frequency is different, this filter, of course, because we work independently for each frequency. So we optimize it for each frequency and multiply it with this vector of m measurements for the frequency f. Okay? So in order to find for each frequency an optimal filter, we need to define the performance measures. So the performance measures, we defined it yesterday. Okay, so we defined the performance measures, signal to noise ratio, input, narrowband input, broadband input, narrowband output, output SNR, narrowband, output SNR, broadband, which we integrated, take summation over all frequencies. We defined the noise reduction factor. As we know, noise reduction factor, it's the amount of noise reduced compared to the reference sensor. Okay, so if we take this output, it contains two components because everything here is linear. So you see, working with linear filters enables us to define things which are easier to derive. So we can write it as X filter desired plus residual noise. So we can check the variance of the residual noise. What is the variance of the residual noise compared to the variance of the noise in the reference sensor? So this is noise reduction factor. And we can also, so we can define narrowband and broadband for each performance measure. And then we can also define the desired signal reduction factor. Okay? So narrowband and broadband, desired signal reduction factor, it means what is the variance of X filter desired compared to the variance of the desired signal in the reference sensor. Like Christmas, snowing. Okay, so desired signal reduction factor, and then we have also the distortion index, desired signal distortion index, narrowband and narrowband and broadband, which means how the desired, what is the mean squared error between X filter desired and X1, what is the mean squared error between them? And it's normalized by the variance of X1. So this is the distortion. As we know, it's similar to what we defined for single channel frequency. And then we can define also the mean squared error, narrowband and broadband, which is the mean squared error between the estimate, the total estimate, and X1. So of course, it includes two parts. One is the mean squared error because of the distortion, and one, the mean squared error because of the residual noise, like this. You see, here. So the mean squared error can be defined as it consists of two components. One is related to the distortion, and one is related to the residual noise. And okay, so if we try to minimize the mean squared error, we'll get the winner. If we try, we can ask which filter here will maximize the SNR, which will give us maximum SNR. So if we write the output SNR, we have this expression. So we saw that any filter that is proportional to phi v minus 1 d, which is gamma complex conjugate of gamma, partially normalized coherence function here. And these are zeta any numbers which are different than 0. We get filter that maximizes the output signal to noise ratio. And we will see that this is for the narrowband, okay? We will see that the other filters that we will discuss, some of them you know, because we discussed it for the single channel, but we will also discuss about LCMV and generalized side lobe counselor structure, which are very important for multi-channel signal enhancement and also for beamforming in the frequency domain. So this will be like new material, so we will discuss this. So except the LCMV and the generalized side lobe counselor, all the filters look like that with certain. So we have this variable. So the only difference between them is with these values. So you see we choose here a scalar value for each frequency. But if we change it, you see it doesn't really affect the narrowband output SNR. You see here. If I take a filter H, a vector for each frequency, and if I put here, again, a certain scalar value, and I multiply for each frequency here, the filter, I multiply it with a scalar value, complex value, okay? So you see that it cancels out in the numerator by the denominator, okay? That's why when you compare, so suppose that I have other filters. We will talk about the Wiener, the MVDR, the trade-off. We will see that all of them are proportional to phi, just like I said here, okay, to phi v minus 1, to this matrix, which is m by m, multiply with the vector of the partially normalized coherence function. So all of them, what does it mean? It means that if the other filters like Wiener, MVDR, and trade-off, if they are, the only difference is this value, it means that all of them maximize the narrowband signal to noise ratio, the output signal to noise ratio, as we will see. The difference, but they don't maximize the broadband output SNR, which is important. Okay? If you remember, if you rehearse the material of the single channel, so you remember that with single channel signal enhancement, we worked with gain for each frequency. And then with gain for each frequency, the output SNR was the same as the input SNR for all the filters. But the broadband output SNR was different. So we were able to maximize the broadband output SNR. So here, because we work with multi-channel, multi-sensor, we can find a vector, a filter, a vector of length m for each frequency, such that it will maximize the output SNR. But any filter that is proportional to this vector, if we multiply it with a scalar complex value, we obtain that the narrowband output SNR will be the same. But it's not equal, it's not maximizes the output, broadband output SNR. Okay? So the differences between the filters are actually, even for this, by this value, and these values, actually the effect of the trade-off between signal distortion and noise reduction, maximization of the SNR, and so on, of the broadband measures is determined by these values. These values are very important. And actually, this is a very nice thing, is that if you take the expression for the output SNR using this, okay, using this vector, you see this is a vector. And you can take any values here, which is proportional to this. So I can compute the output SNR in the expression that we saw before. And this value zeta, we can cancel that in the expression of the output SNR, just like we saw. So if I use this vector and I put it in the expression of the output SNR, when we have M sensors compared to when we have M-1 sensors, and compared to, so we can show mathematically, and this is a nice exercise if you want to show it, to prove it. So the output SNR, you can use that vector, and it's possible to show that the output SNR is a increasing function of the number of sensors. So the more sensors that you use, the output SNR will increase using this derivation. So it's possible to show it, and it's a nice result to show it also mathematically. So it shows that no matter which signals that you choose, always when you add some sensors or you add a sensor, the output SNR will essentially be larger or equal to M-1 sensor. What do you think? Okay, so first, intuitively is trivial, right? Because if you add an additional sensor, you have more information. So it will improve the output SNR that is achieved by the maximum SNR filter, of course. So my question is, when do we have inequality? When it doesn't increase but is equal. So if I add a sensor, additional sensor, and the output SNR that is achieved using the maximum SNR filter is not larger but is equal, remains the same. What does it mean? What? Exactly. So the additional sensor, it doesn't include any information, new information. So it doesn't include the information regarding the correlation. So maybe this additional sensor will not have, think about, suppose that we add an additional sensor and it doesn't correlate the desired signal that is received in this additional sensor does not correlate with X1, with the desired signal in Y1, in the reference sensor. So it will not add significant information that we can use in order to better estimate X1. So it will not add information, and therefore there will be some equality. So remember, you ask a question, if we have sensor that maybe it doesn't add information, maybe the sensor is fault, it doesn't collect real data, but even if we put it somewhere and it doesn't correlate with the signal received in the reference sensor, it means that it's not useful. So it will not add useful information, and therefore we will not improve the performance. Example, did we see this example yesterday or not? No? Okay. So in this example, suppose that we have a signal like this. So we have capital T samples of sinusoidal signal with a constant amplitude and frequency. F0, and the phase is randomly distributed or uniformly distributed on the interval between 0 and 2 pi. So if we have this signal, and suppose that the direction of the desired source comes from theta 0, okay? So the desired source, suppose that this is the array. This is sensor number 1, 2, 3, and so on. And suppose that the desired source comes from theta 0. And there is an interference that comes from the end fire. Okay? So it comes from this direction. Let's call it UF. It comes from the end fire, from theta equals to 0. And in addition, we have thermal noise. Okay. So what do you think if we want to compare the maximum SNR filter? We want to increase the output SNR, the ratio between the variance of X filter desired compared to the variance here, using a fixed number of sensors, fixed number, M, a fixed number, I don't change it. If theta 0 equals to 0, or we increase theta 0, do you think what will happen? Can we improve the performance? If theta 0 equals to 0, which means that the desired source and the interference come from the same direction, do we gain some improvement of the signal to noise ratio if we add sensors? What do you think? Okay, so you said no, but I remind you, I said that we have also thermal noise. Okay, so compared to this component, the directional noise that comes from this direction, we don't improve. If we add more sensors, we cannot reduce this more efficiently because they come from the same direction, so one sensor or multiple sensors, the same performance regarding these noise components. But regarding the thermal noise, of course, we can reduce it to some degree. Not too much, based on the number of sensors, so it goes like the power will go like square root of this, of the number of sensors. So the power will be reduced inversely proportional to the number of sensors, which means that we reduce the noise by the square root of the number of sensors. So we can reduce, but it's not much. We need many, many sensors in order to average the thermal noise if they are independent. So let's see what happens. So in this example, by the way, we can compute the correlation matrices and so on. I encourage you to follow these expressions, okay? I'm not going, because it's an extension of the single channel, but I encourage you to follow this expression, how to compute the correlation matrices, phi v and phi x, and so on. Okay, and we can have an expression for the gain in SNR, specific expression based on the direction of the interference. Okay, so the directional interference. So we have this expression. And I encourage you to follow the step one by one to see that you understand how to do that. So in this example, I assume that the variance or the power of the thermal noise is 1% of the directional noise. So the directional noise is much more significant compared to the thermal noise. Okay? So if we see here the gain in SNR, so this is the improvement of the gain in SNR as a function of M, as a function of the number of sensors for different frequencies. So here the frequency is 0.01, here it's 0.05, here it's 0.1, here it's 0.2 for different frequencies. But let's look at here. What is the gain in SNR? So we see that when, so the blue line is for theta 0 equals to 30 degrees. The green is for 50 degrees. And then the red is 70 degrees. And the last one, the cyan, the light blue, is 90 degrees. So you see that if the direction theta 0 is fixed, we don't change it, it's fixed. When we increase the number of sensors, when we increase M, the gain in SNR increases. See? When theta 0 is fixed. Okay, now it's interesting to see that if M is fixed, if we use a certain number of sensors, M, when we increase theta 0, between, it becomes larger and larger, up to 90 degrees. The spatial separation between U0, between U and X0, and X, which means the spatial separation between the direction of the desired source and the interference, becomes larger. So we are able to suppress more noise. So we increase the gain in SNR. The output SNR will be higher. Okay? So I didn't show here for theta equals to 0, theta 0 equals to 0, which means that they come from the same direction. So you can try it yourself. You have the MATLAB code. You can follow that. You can ask different questions. You can change the signal. So it doesn't depend on the signal, okay? It makes sense because what we try to do here with the filter H for each frequency, what does it do? Any filter, not only the maximum SNR. Here, with the maximum SNR, I show the gain in SNR. But I can show with a different filter compared to the performance measure that I obtained, the optimal filter that obtained, that was derived based on this performance criterion. So if I try to find the optimal filter, so you see the optimal filter, it takes into account the correlation within this vector. What does it mean, correlation between these vectors? Correlation between any two desired components in this vector, and correlation between any noise components in these two vectors, which depend on the configuration of the array and so on. Okay? That's why when we have when we use this correlation, okay, so when we separate them, actually we're able to create spatial filter such that it is directed to the source and suppresses undesired components from a different direction. So as you know, when I talked about overview of multi-channel signal processing, when we get like a steering direction, main beam, or beam pattern that is directed to the direction of the source, there is a certain beam width. So if we use a certain number of sensors, and then we have a certain beam width, and we have also side lobes, which means how much can we reduce these noise components. So what we're trying to do is actually to obtain, to keep the desired signal only from a certain direction, and suppress as much as possible interference from undesired direction. And we try to do that using this filter. So it's spatial filter. So if this direction, the desired direction and the undesired direction, they are close to each other, it's more difficult. Which means that it's more difficult, so the performance will be less. You see, the blue line is below the other one, because the separation, spatial separation, only 30 degrees. So in order to improve the performance, they need to be from different directions. This is one observation, which is obvious. Alternatively, if you want to improve the performance to separation between different directions, you need to increase the number of sensors. Okay? Okay, this is intuitively, it makes sense because we talked about it, about multi-channel. But I also want to show you the relations between different frequencies. What happens when the frequency is higher for higher frequency components? So you remember that even when the array is fixed, suppose that we choose 10 sensors. 10 sensors. And the separation, suppose that the separation between the source, desired source, and the interference is 30 degrees. You see? So for low frequency, the gain in SNR will be something below 20 dB with 10 sensors. Something below 20 dB. But for higher frequencies, if we go to this higher frequency, you see with the same number of sensors, we can get almost 40 dB gain in SNR. Why is that? Why, when we have higher frequencies, we get better output SNR? Exactly. Because it's more directional. So with the same number of sensors, the beam width of the main beam becomes narrow. So when the frequency is higher, the beam becomes more narrow, so we are able to spatially filter different directions better. So we can increase the output signal to noise ratio. Okay, so we have two options to improve the output signal to noise ratio. Either by separating, so if the desired source of interference come from different directions, have more spatial separation, or when we work with high frequencies, so because with higher frequencies we have better directivity of the array, we can separate, the beam width becomes more narrow, so we can separate them better. Or we can actually increase the array, increase the number of sensors, increase its size, and so on. Okay? And then we get better spatial separation. All of that we see here. Okay? And actually it's just an example of the output SNR, but if you work with other performance measures, you get the same increase or improvement in performance. And it makes sense. So just I wanted to show you that when you look at the results, don't just look at the results. Ask yourself, okay, how does it compare to other situations? What is the dependence on the frequency and why? Does it make sense? If we had lower output SNR for higher frequency, then something is strange, okay? So when you get result, try to think, does it make sense? Why do we get it? Not just because we got it, this is the result and that's it. Because it's very easy in signal processing to make a mistake in the implementation, in the MATLAB code or whatever, how you process. And then you get results and then you say, here are the results. But even though you got it, it doesn't mean that this is what it makes sense. So try to think if it's correct or not, and maybe you expected for different results, and try to explain why you expected for different results. This is especially true with deep learning, because sometimes people get results and they consider that like the ground truth. This is what I got. This is the true performance, which is not. You need to be suspicious about everything. Your work and others' work, try to think if it makes sense or not, and try to challenge to do different experiments. Okay? Let's continue. Now with the Wiener. So the Wiener filter is obtained by minimizing the mean squared error. So we saw that the mean squared error, either the narrowband, okay? So we can work with the narrowband mean squared error, which is summation of two components of the mean squared error. One is related to the distortion. The other is related to the residual noise. So we obtained an expression for this. So this is a scalar function of a vector. And we know how to find the derivative or the gradient of this function with respect to a vector and equate it to 0. And then from that, we find the optimal vector. So if we find it, we see that it looks like this. This is the vector, the optimal vector, which optimizes or minimizes the mean squared error, the narrowband. So by the way, if this filter minimizes the narrowband MSC, what happens with the broadband MSC? What will happen? Does it necessarily also optimizes or minimizes the broadband MSC or not? Yes, yes. Why? That's true. Why? If you said yes, I think you know why. But let's share it with the class. Why is it also optimal for the broadband MSC? Remember that broadband MSC is summation of the narrowband MSC. So if it's summation and we optimize each filter for each frequency independently for different frequencies, necessarily we get the minimal broadband MSC. Okay? So the narrowband optimizes not only the narrowband MSC, but also minimizes the broadband MSC. Okay, and then you see that is, okay, so it looks like this. So I want to compare it to the maximum SNR, okay? So first I want to show that this Wiener filter also maximizes the signal to noise ratio, the narrowband output SNR, not the broadband output SNR. Why? Because we saw that looks like that. So it's proportional here. So in order to do that, we will need to show that the Wiener filter is proportional, the narrowband Wiener filter is proportional to this. Phi v minus 1, complex conjugate of the partial coherence between x1 and x. Okay? So let's write it here. So we saw that any filter that is proportional to that maximizes the output SNR. Okay. So if we derive the Wiener filter, we see that it looks like this. So it doesn't look like proportional to phi v minus 1. So it's a question if it maximizes or not. But we will see that we can have different formulation to the Wiener filter. So we will continue. But here it doesn't show like it maximizes the output SNR. But we can define different things. Okay, so first we can show that we can write the Wiener filter like this. This is a different expression based on the normalized coherence matrix. So if we normalize it, so we have something like this. And this is a nice formulation for the Wiener filter because it shows like it's a multiplication of two components. One component, this is the gain that was derived for the Wiener filter when we used single channel. For the single channel Wiener filter, it looks like that. Input SNR divided by 1 plus input SNR. So this is the gain that was obtained for single channel. And this part is a vector that takes into account the spatial filtering. So it looks nice, this kind of observation, how we define this vector, the filtering vector here, Wiener filter, by combining single channel Wiener filter and spatial filter. It's nice. It's nice to see that. Let's continue. Let's see if we can have different expression for this vector and get some insight from these different expressions. So we can write also the Wiener filter like this. Okay? So if I give you different expression, what did I do? Instead of phi x, you see this is very nice, right? It's a very nice way to write different expression for the same filters using your model. So what we did here, you see, we can write that instead of this is complex conjugate, so it looks like that. Okay. If I write it H Wiener F, we can write it as phi x1 F. Okay, I will go backwards. Phi y, the coherence function, minus 1 F, complex conjugate x1 x Fs. Okay. So instead of this vector, I can write something different. You see, this is the partially normalized coherence function. So I can write it like this. I can write the Wiener filter by the coherence between x without the normalization, because phi x1 multiplied with this partially normalized is simply the coherence between the vector x and x1 complex conjugate. So I can write this vector as the coherence function or correlation function or matrix and multiply it with a vector of 1 and all zeros. I remind you that the vector II is defined as 1, zeros, all zeros of length m. So you see that this correlation matrix, if we multiply it with 1, we have a vector. This is the vector. Okay? which is very nice, because what is phi x? This correlation matrix. What is it? This equals to x multiplied with x h, f, expectation. So if we take this matrix and we multiply it with this vector, we get the correlation between the vector x and only the first component, which means that x1 complex conjugate. So you see, so we replace this vector with this vector. Matrix multiplied with this vector. Now, instead of phi x, we can write that phi x is phi y minus phi v. So we get this expression. And my question, you are supposed to answer by now. Now you're, after 6 days, you're an expert, right? Okay, so why do we need different expressions for the filters? Why not, if we have one expression, that's it, we use this one. Why do we need other expressions? Can we get different performances with different expressions? Okay? So actually, different expressions will result in different performances. What are the differences? Okay, so when we ask this, think about what do we have. So this expression, this filter depends on phi y minus 1. So we need to invert this matrix, the correlation matrix of the measurements, of these measurements. So we find these correlations, and we need to invert this matrix. Also, we have it here, phi y minus 1. So we need this same information in both expressions. But here, we need the correlation between the vector x and x1. So we need the correlation between any desired component in these sensors compared to the desired signal components in the reference signal. Here, we don't use it. We use the correlation matrix of the noise components. So you see, we use different information. So if you know the exact values of these matrices or vectors, it will result in the same performance if you know exactly, if you obtain the true values of these matrices. But if you estimate it from limited measurements, when you estimate something, so there are different differences between the estimations. Because you can try to estimate this, but you can try to estimate the noise. And then you will get different results because these are estimations. So different estimation processes, when you put it in an algorithm, based on limited data, you will get different results. So pay attention to that. It's important. So sometimes it's important to derive different expressions to see how we can use estimates that we can estimate maybe more reliably. Okay? Maybe we can estimate this better than more accurately than estimating this part. So it's important to have different derivations of estimators, of filters. Okay, let's continue. Now, using Woodbury's identity, we can replace the inverse of this matrix by this expression. If you are not familiar with that, please look at the internet. What is the Woodbury identity, and try to prove this relation. Anyway, if we substitute, instead of phi y minus 1, we put it in the expression, we get a new expression, like this. And we can also rewrite this expression like this and like this. So you see we have different expressions for the Wiener filter, even though it's a vector of length m. Okay, what do we see here? Okay, this is very nice to see it. Okay, here, do you agree that the denominator is a scalar? Scalar, complex value, scalar, right? And here we have a scalar. So if we compare it to the filter that maximizes the signal to noise ratio, you see it is proportional to phi v minus 1 complex conjugate of gamma x1x, the covariance function between x1 and x. So you see we got some relationship between the Wiener filter and the maximum output SNR filter, which means that the Wiener filter not only minimizes the narrowband and the broadband output mean squared error, it also maximizes the narrowband output SNR, because it looks like this. From this expression, you couldn't know. But from this expression, you know that. That is all. What do you think? Do we also obtain maximum broadband output SNR using this filter? Yes or no? Yes? Okay, let's think. First, you said yes. More answers? Some yes, some no, or everybody thinks yes? No. Okay. So each one of you maybe try to explain. But before that, I repeat, the Wiener filter minimizes the narrowband MSC, it minimizes, and then it also minimizes the broadband MSC. Why? The reason? Because the broadband MSC equals to summation of all narrowband MSC. That's why if we minimize the narrowband MSC, we also minimize the broadband MSC, because we can work on all frequency independently. What happens with the output SNR? So the output SNR, the broadband output SNR compared to the narrow output SNR, narrowband output SNR. If we compare these two, can we write here equality? No. Therefore, if we maximize, using here, if we maximize the narrowband output SNR using here, using this filter or this filter, still we don't necessarily maximize the broadband output SNR. Okay? In order to maximize the output SNR, you need to choose these values in such a way that the broadband output SNR will be maximized. Here we don't have it. Okay? And actually, using some examples, you can try to find estimates and see and check, verify that you get different results with different expressions. Because sometimes people think, okay, I get a different expression. It's not important. Actually, it's very important, because you can get different estimates from limited data, from real data. And then you get different performances, and you need to think. Just like I talked about single-channel speech enhancement, also I talked about obtaining differences, and we talked about the models and so on. So also here, it's a very, very nice, if you repeat the example that is related to what we show here, and instead of taking these matrices phi x and phi x and phi y and phi v, instead of taking it from the true signals, you take it from noisy measurements, realization of the data. And you try to estimate it. And then you put it in different expressions and see the differences. This is a beautiful exercise. Okay? So try it. So we will continue from here. You deserve a break. 10 minutes. 10 minutes is okay?